Hello everyone. In this video, I'm going to introduce Monte Carlo methods. I'm going to start off by describing what Monte Carlo methods are, and then we're going to work through a fairly simple example of using Monte Carlo methods to determine the probability of different outcomes. So just as an introduction here, I've got a document that I'm going to go through. Monte Carlo methods are a class of computational algorithms used to model and analyze complex systems that may be difficult or impossible to solve analytically. These methods rely on repeated random sampling to obtain numerical results, which make them especially useful for evaluating uncertain, variable, or probabilistic phenomena. The Monte Carlo methods were actually designed and developed around gambling. That's why the title of the method is Monte Carlo. It is referencing Monte Carlo in Monaco, kind of a gambling mecca. And so we're using these techniques to determine the likelihood of different outcomes in environments that have randomness. So the three steps in a Monte Carlo approach is the first step is we define a probabilistic model. The process begins by defining a mathematical model of the system incorporating key variables and their distributions. For example, in financial modeling, investment returns follow a normal distribution with a specified mean and standard deviation. After we define our model, we generate random samples. The Monte Carlo method then generates a large number of random inputs for the defined model. The sampling might involve generating thousands or millions of instances of variables based on their probability distributions. The randomness allows the model to cover a wide range of possible outcomes and behaviors of the system. And then finally, we simulate and analyze outcomes. Each set of sampled variables represents a unique run or simulation. The model is run for each set, and the outcomes are recorded. After many runs, statistical analysis is applied to the aggregated outcomes to estimate metrics such as the mean, the variance, or the confidence intervals. Monte Carlo methods are widely used in finance, engineering, physics, and operations research. They're particularly valuable for risk assessment, optimizing complex systems, and decision-making under uncertainty. For example, in finance, Monte Carlo simulations help estimate the future performance of an investment portfolio by modeling various market scenarios and calculating potential gains or losses under different conditions. In engineering, Monte Carlo methods are applied to test the reliability and failure rates of complex structures or systems under a range of conditions. In the example we're going to work through, we're going to take a look at rolling a pair of dice, going back to the original Monte Carlo idea of gambling, and we're going to see how multiple simulations of rolling a pair of dice generate different outcomes. And then we're going to observe the likelihood of different outcomes, in other words, different rolls. And we're going to then compare that to what we know a pair of fair dice should give us. Okay. The difference between this, like I mentioned before, simple example, and a more realistic use of Monte Carlo analysis is that under a more realistic use of Monte Carlo analysis, we can't automatically just calculate the likelihood of different outcomes occurring. But that's what we're going to start with in this example. So let's go ahead and open up Excel. We're going to create a new workbook here. We're going to start by showing all the different possible outcomes from two dice, the rolling of two dice. So I'm going to have my first die here, die 1, and my second die here, die 2. And for my first die, if I roll it, I can get either a 1, 2, 3, 4, 5, or 6. And here we're using the idea that it is a 6-sided dice. I know that there are 20, 30, 40, 50, 60, 100 sided dice for people that do a lot of gaming. But in our example, we're going to keep it simple and just 2 dice with 6 sides each. So here in my table, I'm going to go ahead and highlight the table just to show what we're filling in. And I'm going to put in my first cell, and this is cell C3. I'm going to put in equals C, and then a $sign, and the number, selects, and then the number 2 to select C2, and I'm locking in place my row but not my column, plus, and then I'm going to put in a $sign, and then B, and then a $sign, or not a $sign, sorry, and then the number 3. So it highlights cell B3. It locks in place the column but not the row. Press enter. So if I rolled 2 dice and I got a 1 on one of those dice and then 1 on the other, my sum would be 2. The total for those 2 dice would be 2. I'm going to pull that across, pull it down, and this gives me all of the potential outcomes for rolling 2 dice. So here, if I roll a 6 on one, 6 on the other, I get a 12. If I roll a 4 on one and a 3 on the other, I get 7. So now we're going to use the COUNTIF function to determine the number of times that a single number shows up in our table up here. So I'm going to put down here sum, count, and then the probability. We're going to calculate the probability of specific outcomes with our rolls. So I'm going to put down here 2, 3, 4, and I'm going to drag this down all the way to 12 because these are our possible outcomes for rolling the pair of dice. Here we go. There's not a 1 here because if I have 2 dice and the minimum number on each one is 1, then the minimum number of rolling them together is a 2. Here I'm going to use the COUNTIF function, so I'm going to put in equals COUNTIF. My range is going to be my yellow area up here, my table. I want to lock in place my cells because I'm going to drag this down. And then I'm going to put in a comma. My second argument here is the criteria. In this case, I want to count the cell if the value in the cell is 2. So I'm going to select my cell C11 here. I'm not going to lock anything in place there because I want that to change as I drag this down. And so this is what my function looks like in Excel. I'm asking it to count the number of cells in my yellow area here if the value is 2. And so we get a 1. And that's what it should be. There's 1, 2 here. I'm going to drag this down now. And so we can see here that the most common number is 7. So 1, 2, 3, 4, 5, 6. There are 6 sevens. So if you're rolling a pair of dice, the most likely combination that you'll get will sum to 7 because there are many ways to get to 7 by rolling a pair of dice. Finally, we're going to calculate the probability here. So there are 36 possible outcomes, so 6 multiplied by 6. We're going to divide each of our counts by 36 to get the probability. All right, so this is what our outcome looks like. Like I said, the highest probability is to get a 7, and that you have a 16.67% probability of getting a 7, or a 1 in 6 probability of getting a 7 when you roll a pair of dice. The least likely probabilities, least likely outcomes are 2 with a 2.78% probability and 12 with a 2.78% probability. So we know what the outcome should be when we roll a pair of dice. Now we're going to add a little randomness, okay? And we're going to have multiple simulations. We're going to start with 100 simulations, which may seem like a lot, but that's not very many, and Excel or whatever program that you're using has the capacity to do many, many more than that. We're going to then increase the number of simulations that we have to show that by increasing the number of simulations, we get a more accurate result. So here I'm going to put in my test. It's going to be the number of tests that I have, my first die, my second die, and then the sum of the two outcomes. So I'm going to put here my first test. Here I'm going to use the function rand_between. I'm using this function because there is a minimum number that you can have on a die, on one die, which is 1, and there's a maximum number of 6. And so I want my number to be a random number between 1 and 6. So that's what I'm going to put in there, rand between 1 and 6. And then for die 2, I'm going to put in equals rand between, again, 1 and 6, because that's the same thing is true for my second die. Now you may not be getting the same numbers here. In fact, I hope you're not, because these should be random. And then I'm going to put in the sum. I'm just going to add these two together. And you can see there, when I pressed enter, it changed the first die. Okay, because it's recalculating that rand between number. I'm going to show you here in a minute how to turn that off. I don't want to turn it off right now, and I'm actually going to leave it off for this example, but I'll show you how to turn that off, because as you get into more complex models, that can be a strain on your system where you can manually have it recalculate your outcomes. So let's go ahead, and I'm going to make 100 tests. I'm going to start with that just to show you what the outcomes looks like, and then we're going to increase that to 1,000. So I'm going to drag this down to give me a list of 100. There we go. Now you could get a pair of dice and you could sit at a table and roll those dice 100 times to generate this data. But because we're using Excel and rand between, our outcomes should look similar to doing that test. Okay. So here I've put in my die 1, my die 2, the random rolls from each of those, and then adding them together. We're going to duplicate this table that we have over here, or the second one that we made up, with the sum, the count, the probability. And then we're going to compare the outcomes. So I've got sum, count, probability, and difference. The difference is going to be the difference between the probability for our simulations versus the probability that we first calculated for each possible outcome. So our sums are going to be, again, 2 through 12. And again, you can see here as I put something in a cell and press enter, it changes the values that are the rand between values here. Our count, so here's where I'm going to put it in count. If my range is going to be the values in column M, so I selected cell M3. I'm going to press Control Shift and the down arrow to highlight all of those, and then comma. I'm going to go back up here. My criteria, like it was before, I'm just going to select the sum value here. There we go. And then close my parentheses. I want to lock into place my range because I'm going to drag that down. I don't want it to miss, the top values in that range. I'm going to press enter. The probability in this case is the count, the number of tests. So I'm going to put in here equals. And because I have 100 tests right now, I'm going to equals divided by 100. We're going to change this later on. I'm going to make that into a percentage. And now I'm going to put my difference is equal to the and I'm going to put in, I'm going to use the absolute value of the difference because I want to see what just how much my Monte Carlo analysis is off from the actual probability of something happening. So I'm going to put in your equals ABS, open parentheses, so it gives me the absolute value, the value in the probability minus the probability from our first table, and then close parentheses. Notice I'm not locking anything into place here because I'm just going to drag this down. So I have my count, my probability, my difference. I'm going to drag it all down here. And then finally what I'm going to do is just make that look a little nicer. Okay. So we can see here, my tests aren't great. There is, I mean, you know, the outcomes look similar to what we had originally. The most likely outcome here, though, is 6 instead of 7. So we see more 6s in our 100 tests than we do 7s. And we know that 7 should be the most likely outcome. Okay? The ones that are off the most, that 6 is the one that has the biggest difference between our simulations and our outcomes below. This one down here, 11, we see that show up 8 times, or 8% of in 8% of cases, where it should just be 5.56% of the time. Our 2 and our 12 are the least likely outcomes, well, and 3. And that's similar to what we would expect from the overall probability of that occurrence happening. So now, kind of take a snapshot of this in your head, and now we're going to increase the number of our tests to 1,000. Okay, so I'm going to go down here. I'm going to grab the last few here, and drag that down, and we're just going to cruise down for a ways here till we get to 1,000. And while I'm doing this, I'll just mention that there are methods using Visual Basic to do this automatically. I'm not going to go into that in this video though. So I'm going to drag this down to get 1,000 different tests. I'm going to scroll back up here. I'm going to grab these 3 cells. I'm going to drag them all the way down to my 1,000 different tests. And now I need to make one last change to update my table over here. Before, I calculated the probability divided by 100 because we had 100 different tests. Now I'm going to put in 1,000 here. And then I need to do one other thing. I apologize. I need to change my COUNTIF function to go all the way down through all of my values here. So I've highlighted M3. I'm going to press Control Shift and then the down key to highlight all of them. Now I'm going to lock into place my range. And then I'm going to pull this all the way down through 12. And I need to pull this one down. That's why my values are getting kind of strange here. There we go. And so now we see this is an improvement on what we got before. We actually had some pretty large differences. Now our largest difference is this 3 here. It shows up 78 times, or 7.8% of our test. And the difference here between what we would expect for a pair of fair dice is 2.24%. So this is an improvement. We could take this out to 10,000. We could take this out to 100,000 different simulations. And as we increase the number of simulations, we would get closer and closer and closer to our original probability distribution. So this is an example of Monte Carlo analysis. I wanted to show you one last thing, and this is how to turn off the automatic calculations. So if you want to do that, go to File, go to Options down here below, and where it says Formulas, you want to go where it says Workbook Calculation. You can change this to Manual, and if you don't want it to recalculate before saving, just click that off. And in this case, pressing F9, if your keyboard allows this, will automatically recalculate the formulas, or not automatically, will manually recalculate the formulas for you. Please let me know if you have any questions about this video, and I hope you have a good day.